In this video, we will focus on definite integrals, which we'll solve using integration by substitution. When we want to evaluate definite integrals while using the substitution technique, we have to be careful about the limits of integration. A definite integral has the form the integral of some function dx from a to b, and we know from the fundamental theorem of calculus that if we can find the antiderivative of the function small f, capital F, then we can plug in the upper limit b, the lower limit a, take the difference, and this will give us the value of the definite integral. When we're doing u substitution, the variable is transformed from an x to a u, and that transforms the values of the limits. So we need to transform the limits of integration to be in terms of the new variable u, and we use these transformed limits in the transformed integral. Let's take a look at an example where we solve a definite integral using this concept. Let's look at example 4. We have the integral from 1 to 3 of 2 divided by 1 plus x dx. Now, this one is not quite as obvious as some of the other substitution integrals that we've seen, but we can solve this using substitution if we choose u to be the denominator, 1 plus x. Now let's follow through the steps. Take the derivative of u. The derivative of 1 is 0. Derivative of x is 1. Solve for dx. Dx, in this case, equals du. Now we can substitute into the integral. Notice that I'm not writing the limits of integration yet. We need to transform them. So I have 2 divided by 1 plus x, which is u, and dx turns into du. Now, in the original integral, the 1 and the 3 are x values. These are values along the x-axis, x equals 1, x equals 3. When we transform the integral to be in terms of u, we're working with a different variable. The values 1 and 3 are values of x. We need values for u to be the limits of the new integral. We get those values by taking the expression that we chose for u, plug in the x equals 1, plug in x equals 3, and we get the proper values for u. There are two steps. For the first step, we say if x equals 1, we take the lower limit. U, well, u is 1 plus x, so we do 1 plus 1, which is 2. That is the new lower limit of integration. Do a similar procedure with the upper limit. If x equals the upper limit of 3, u is 1 plus 3, which is 4. That is the new upper limit of integration. If we use the 1 and the 3 from the old integral, we will have the wrong values for the new transformed integral. Now that we have the appropriate limits of integration, let's finish the problem. The integral of 2 over u is 2 times natural log of the absolute value of u. We plug in the limit 2, we plug in the limit 4, and we get our final answer. 2 times the natural log of 4 minus 2 times the natural log of 2. Notice that we do not substitute back in terms of x. When we transform the limits of integration, we leave the integral in terms of u. We use the transform values for u, and our final answer is there. Let's try one more example, and we'll also visualize what this integral looks like using Desmos. Example 5, let's take the integral of natural log of x over x from 1 to e. This problem is not very obvious how to solve using u substitution. We're looking for an inner function whose derivative shows up somewhere else in the integral. That's rather difficult to see on this one. We could be tempted to pick u as the denominator in this case. That's what we did for the last problem. But if we choose u equals x, all that will do is transform the entire problem to be in terms of u, and it will look identical other than that. So let's just make a little note here while we're on the subject. Never choose u equals x in u substitution. It will never simplify the integral in a usable fashion. All right, so if we can't choose u equals the denominator, really there's only one option left. We want to choose u to be the numerator, natural log. Now notice, the derivative of natural log is 1 over x. 1 over x is in this integrand. So let's see how this works out. Follow the steps of u substitution, take the derivative of natural log, which is 1 over x, and now solve for dx. We multiply both sides by dx, multiply both sides by x, we obtain dx equals x times du. Substitute these values into our integral. The natural log turns into u. We still have the x in the fraction. And then dx turns into x du. The x's cancel. And now we need to transform the x limits of integration to be in terms of the new variable u. So we follow the same steps that we did in the previous example. If x equals the lower limit of 1, u, that's the natural log of x. So u will be the natural log of 1. The natural log of 1 equals 0. By the way, this is an important value. We should be comfortable with the fact that natural log of 1 equals 0. That's something we want to remember. And we do the same procedure with the upper limit. If x equals e, u is the natural log of e. Natural log of e is 1. This is another value that we want to be familiar with. These are two expressions that we'll see from time to time, and we want to be comfortable with them. So the 1 for the previous integral is transformed into a 0, and the upper limit of e is transformed into a 1. This is our new integral. The integral from 0 to 1 of u du. All right, take the antiderivative of u squared divided by 2. We'll plug in the 1, we'll plug in the 0. 1 squared divided by 2 minus 0 squared divided by 2. 1 squared is 1, divided by 2. We have 1/2 minus 0. The answer is 1/2. Notice once again that we do not return to the original variable x. When we're performing u substitution on a definite integral, we leave everything in terms of the new variable u. We do not write the answer in terms of x. Let's visualize the relationship between our original integral and the transformed integral using Desmos. Here we have a graph of natural log of x divided by x, and we're highlighting the area from 1 to e. It's that blue shaded area. When we transformed this integral, we were integrating u, and we can just graph this as y equals u, and the integral was from 0 to 1. That purple area is the same area as the blue area. Purple area comes from the transformed integral. The blue area was the original one, but using integration by substitution, the two integrals were equivalent.